Okay, so we started the stencil example. We ended the stencil example session with a question on how well this code that we implemented really scales, right? So, and last night I ran the code on Daint, scaling on up to 2048 cores. Sorry, not cores, nodes, right? And these are the results. So the blue line is the actual performance in gigalattice updates per second. Okay, I'm here. That's the usual metric that you want to use there. And the red line, so the scale is on the left-hand side, and the red line shows the parallel efficiency of this code, right? Which is with the scale over here. Okay, so yeah, not very good, right? I mean, it's decent. We get around 56% parallel efficiency there, which is a nice first result, right? So the question is, can we do better? Okay.
But you can't run it on one node, right?
Hmm? Oh, that's weak scaling. Sorry.
Oh, that's weak scaling.
Sorry. That's weak scaling with 30K times 30K grid points per node.
Yeah.
Okay. And I just scaled up the y direction to not run into the bandwidth problems if I scale up both dimensions due to the partitioning scheme we implemented. So yeah, that's the weak scaling results. Of course, you're interested in strong scaling as well, right? So I also did a small strong scaling experiment with 30K times 960K grid points. You can see that it scales fairly decently up until 768, 86 nodes, right? Huh? 768. 768. No? 768 nodes. And then it just drops, right? The scalability drops. So problem is, it's a fairly small problem still, right? On 1K nodes, we have around 1,000 grid points in y direction, and on 2K nodes, we have 500, of course, in the order, right? So it's fairly small, and the communication and the weighting on the communication dominates there, right? So. But up until 768, we do have a fairly well scaling. You see that you have an efficiency of a little bit over 1 here, over 100%. The reason for that is, actually, I don't know why. It seems a little odd, right? Maybe it was due to the partitioning or networking that you had a little different network loads there, so you might want to repeat the experiment a little more often on a different allocation with different nodes, so that might be a factor here, right? But scalability is there, so that's really nice. However, looking at the weak scaling, the efficiency doesn't look so good. Right? We have around 60%, and the question is, can we do better? Right? So in order to answer that question, we really need to look at the code. Let's see if I can find it real quick. Sorry. Here we are. So the version that I ran is this parallel_2, which is the first distributed version. And if we, so the limitation in scaling is probably the communication, right? So what we have here is really synchronous communication. So we wait until our neighbor delivers the result. So we really have a very tight coupling there and a very tight synchronization, which is limiting the scalability, obviously, right? So one thing we could do about that is to really not immediately wait until we received our neighbor, our rows, but to do some continuation style programming. Or what I would like to introduce first is to add oversubscription, right? So we implemented this nice communicator which is independent on the number of localities that we actually use. It just sets up the channels in order to do the neighborhood, the boundary exchanges, right? So, well, why not just instantiate a bunch of those communicators, right? And say we have 2 or 4 or 8 or 16 of those partitions on one locality, on one process, right? This should get us going, even though we wait here, right? Even though we wait here, this should get us going to hide the latencies that we have in order to receive the messages from our neighbors, right? And the next thing is, of course, to implement futurization. That is to actually not directly wait until our neighborhood communication is complete, but actually use the future that we get from this communicator and do the line update and setting of our bottom row only when the communication happened, and in between turn this for loop into a synchronously running loop, and that way we can actually overlap very easily the communication with the computation, right? So just adding the oversubscription is in the _3 example, right? And I'm stupid now. All right. Right. So instead of using the number of localities for our partitions, right? We scale the number of localities with the number of local partitions that we want to use, okay? And use that as the total number of partitions, and divide our global grid points by the number of partitions. And for each of those partitions, start a worker thread that works on its local partition, right? And in that worker thread, we do the very same as if it was its own locality, right? So we assign it a unique rank and tell it how many partitions there are and its local sizes. Okay? And that's it. And the rest is really just the same. So the worker function here contains exactly the same code as if it was on if we have done one partition, right? So that's really nice. So implementing oversubscription is very easy in that context. Now, the futurization is a little bit more complicated because you have to work with the you have to work with this continuation style parsing, right? So what we first want to do is we want to create a future for each step. So we only execute the next iteration once the previous iteration has been completed. Right? At the beginning of our algorithm, of course, the step has been completed, so we just construct a ready future. Right? And then when the iteration starts, we say whenever the previous step has been completed, we attach a continuation which performs the next iteration, right? And what you see here is we capture the policy, our current iterator and our next iterator by value, right? So capturing the current and next iterator by value is actually important, right? Because if you look at the end of the for loop of our number of iterations for loop, we swap current with next, right? If we would take it by reference in some way or another through a pointer or whatever, shared pointer or whatnot, right? We would run into race conditions because we have the reference and the reference is changed all the time, right? So we don't have any thread local variable there. So for each of those continuations, we want to have a fixed current and next pointer. So we need to capture it by value then. Capturing by move would be fine as well, but iterators are very cheap to copy, right? And then we can use the future that's been returned from the communicator and attach a continuation to it, right? And this continuation takes as a parameter the future which contains our boundary, right? And then once that continuation has been executed, once this continuation is being executed, well, we do the same as before, right? We just update our top row, and once it's updated, we set it to our lower neighbor. But this is now completely asynchronous and runs as soon as the communication happened. Okay, and this line here. So if you imagine that the body of the continuation is away, so this line here is executed immediately. So it returns immediately, and we can move on, right? And we can move on to update our interior spatial domain, which is just issuing the for loop again, the parallelization, which then returns a task, because the policy that we employed here is the parallel task policy. Okay. So top neighbor communication, interior update, and the lower neighborhood communication is completely asynchronous, completely parallel to each other, and it's being executed as soon as the data that it needs to run is available, right? And then the continuation just returns a future which becomes ready when all of those three futures that we need to update our domain, our partition, are ready. So that's when the next step can be executed, right? And that's how you would employ the futurization, right? So let's see what the impact of that is if we add it to our code. So that's the influence of the oversubscription on the weak scaling experiment on 1K nodes. Okay, the blue line is the gigaloops updates per second if we just use oversubscription. Okay, and the red line is oversubscription plus futurization. You can see that on a 1K node, having futurization alone gives a small performance benefit, right? But adding the oversubscription, well, we gain a little bit, but it drops down after a certain amount of the number of local partitions. And the reason for that is because we just add more work on the different workers, right? And they get a little bit overwhelmed. But we are going to demonstrate that with the performance counters, not at the scale, but you can see that already on 2-node scale. So that's nice. We can play around with it a little bit. Okay. The strong scaling influence is very similar, but it drops fairly quickly. So here the number of local partitions doesn't have any good influence. So adding more partitions is actually making it worse, simply because if we add more local partitions, we divide our domain even more in the y direction, right? So we lose grain size. We lose useful work we can do on the partition themselves. Okay. If you'd look at the strong scaling for a smaller node count, you could see a similar effect than with the weak scaling. And this Google document spreadsheet is linked in the slides, so you can actually look at the data. So all the data is there. I will also update upload the batch script I used to run those experiments. But you can export the data and play around with it a little bit on yourself, produce other graphs than I did to see the different scalability. So I specified a too low small time to have the jobs completed for the 2K node runs. I'm still waiting on the new job to get through the queues.
Rather than linking to the Google Docs spreadsheet, it would probably be a better idea to put the spreadsheet in the repo,
yeah,
so that it survives beyond when this disappears. Yeah.
Good thinking. Right. So let's look at the scalability, adding the oversubscription, and for the weak scaling experiment, we can see that we are now able to reach 90% efficiency, even at scale. Well, this here is 86%. I can't. 85.9% parallel efficiency for the final version, which is a pretty nice result, right? Considering the terseness of the code. For strong scaling, unfortunately, we lose in parallel efficiency for the higher core counts, right? But we get much better performance. So it would be interesting if we run it on a bigger problem size, what the behavior then would be. But all in all, you see a similar quantitative behavior of the curve, so that it stops scaling after 1K nodes, right? But the parallel efficiency is a little bit lower because the version on 16 nodes is already a little bit faster, so that we lose a little bit of efficiency there. But scalability is still there. And we are in the range of 66% for 768. Which is still, I think, a nice result considering the small problem size. Okay, so that's what you can get when writing applications within HPX, I think. So it does scale. And I would suggest that we look at the different performance counters to see why the first version didn't scale, what influence AGAS has, what influence the number of partitions have, and so on, to give you an idea on how to use the performance counters and how they relate to actual runtime. So, yeah. Any questions on this data?
What's the difference between the green and the orange?
The green is the parallel efficiency, and the orange is the actual performance metric.
Okay.
Of course, you could go to higher, larger domain size.
Yeah.
And push it out.
Yeah, that will push it out, yeah.
So I don't think it's really fair to look beyond 768 anyway.
Probably not, no.
Local domain scanning.
Probably not, yeah. I just wanted to see if it works and what the behavior is there.
I'm slightly curious. The yellow and the blue, they go up to about 1,000, but the green one is coming down fairly linearly.
I might have made some mistake when doing the formula. It looks strange, doesn't it?
Something's not right about it, because it has clearly a knee in the overall performance, but the speed up, or the efficiency is linear. And I would expect there to be a knee in the efficiency as well, but
I have to look at the spreadsheet calculations again.
Okay, is there something which we can set the guys doing to start running the stencil example whilst you... Because I would be happy to generate a trace file of a particular scenario if
right.
you...
Let's make you generate the trace files, and I suggest that you work on the stencil example and print some performance counters you think might be interesting, and play a little bit around with the parameters to see the performance implications.
You might want to suggest the performance counters that they want to print out, like, for example, the idle rates. Because I doubt that they can remember what all the performance counters are.
Oh, right. So the idle rates is usually a very nice performance counter to see how well the application really performs and how much time it spends doing useless work. Then you were particularly interested in the impact of AGAS, right? So you can print the AGAS performance counters. It's especially the AGAS cache is interesting, right? So you can see how much cache misses, how much cache hits, and so on there are, and how much you actually had to ask a remote locality about resolving the ID. So we had to have extra routing.
Now, I've compiled my version of HPX and my version of the tutorials. You haven't pushed anything to tutorial examples like in the last hour or two, have you?
No.
Okay,
No.
so I should be up to date, and I'll just check that everything's built. So I've compiled with the profiling on Daint. I've used the profiling module and compiled all the examples, and I think I've got an allocation. Yes, I'm in an allocation. I've got 4 nodes. So if I were going to generate a profile from a 4-node job, I would want, am I running the stencil, oh, hold on. do I want stencil 3 or?
Whatever you feel. I mean, it would be nice to have a trace file for stencil 2.
Stencil 2 using NX is, oh, and I should point out that these lines here, by turning on, I actually probably don't need Apex Tau. I just need the Apex OTF because I want to generate open trace format traces, but I'll leave Tau on anyway. And this will impact performance a little bit, so the results will be slightly different from a pure release, but it will at least give us an idea. And I want profiling, actually I really just want the OTF flag, but I'm just going to enable them all because I haven't used this for some months. There was a previous version I played with and I've kind of forgotten the settings a bit, so I'll just enable everything and the screen output. And then I want something like 30,000 on NX. And NY, I want 4 localities, 120,000.
Yeah.
NY equals. And do I want oversubscription? I just want 1 local partition per node. So I don't add a parameter. I run that.
The second version doesn't have oversubscription.
Ah, okay, because we're doing stencil 2. So this is just 1 partition per node, and it's not futurized. So what we're looking for is hopefully we're going to see the gaps between the tasks, which is the reason why we don't reach 100%.
That's the idea, yeah.
And it appears to be running. Will we have to wait a long time for this, or is it just a few seconds?
100 dots, about a minute.
100 dots, okay, about a minute. And I don't know if, are you guys playing along with this or running examples, or are you, okay, fair enough. Because we'll be testing you on how to attach GDB to node 3 of this in a minute. And
because it will crash. So if you experience a crash, you might, so I was running into small difficulties last night when I generated those results because one of the hot fixes that I thought that would fix a particular problem actually led to the whole program to not work at all due to a race condition. So we had to revert and roll back this change. So I think John compiled it this morning again, so you might need to recompile your examples if you haven't done so. And
in this brief pause, I'll mention there are some settings here which Apex is dumping out, which are to do with throttling. And the reason is because Apex isn't really just for generating trace files of your task-based programs. There's actually a whole lot more going on in Apex, which is that you can have callbacks within Apex when tasks are run and they register themselves to say I'm running a task and they generate the traces. You can also pass extra information and allow Apex to query the performance counters, and it can do throttling of things so that, for example, if you wanted to limit the amount of cycles you're using or the power you're using, and there's extra stuff coming out here. We're not touching that at all today, but if you're interested in that at all, then the documentation, which is not very extensive, has some information. And that looks like it's come to an end. It dumps out a bunch of statistics initially to tell you how long it's spent in each of the actions, in each of the tasks. Some of the Lambda functions are tasks, but Lambda functions are usually unnamed functions, and they don't necessarily generate anything useful that can be registered. But inside all the async calls, any of the functions which are registered as actions in some way, they get called, and Apex will dump out the sort of summary of what's going on in there. You can get some information from there. I'm going to skip through that and go straight to what I hope. Okay, we've got profiles generated, and inside this directory which is generated, we'll have an actual trace file, which, with a bit of luck, and thanks to Jean-Guillaume, I've installed Vampire on my local machine. And what I'm going to do is I'm going to do an SC. I'm going to copy the data off Daint, and I'm going to copy it to stencil 2 on this machine. And then I'm going to load up Vampire. And OK, that's finished copying. And I'm going to open a local file, which I hope is going to be stencil 2. There we go. And then I want to load the open trace format. And assuming nothing crashes, then we get a trace file. And this is the first time I've tried it on multi-node. So I'm not entirely sure. How many nodes? We ran 16 threads per node. And at this point, I'm expecting to see 16 times 4 threads in here, but I'm only seeing 1 node's worth.
Uh-huh.
Okay, but the important thing is here, if you look at the individual tasks, there's quite clearly a synchronization issue going on here, which is leaving gaps between, that's main, that's not right, that shouldn't be main, hold on.
Oh, main is fine because
Main is
everything's
fine.
run out of main essentially.
Because you don't have any actual tasks.
yeah.
Okay, so what's happened is, because we haven't actually given any of our little subtasks specific names, they're all running inside the HPX main task, and so they're being registered with Apex. And that's because at the moment Apex is still a fairly new library, and what we need is a way of saying, every time we enter a Lambda, for example, flag this as a new little subtask and give it a name that we can then see in here. And then you would probably see this broken up into a whole bunch of slightly smaller things that are going on. So what I'll try now is, if I zip back to Daint and I try running the same settings, but this time I want to run, if I run parallel 3 with exactly the same parameters, is that a useful?
Parallel 4, because
Parallel
then you
4.
see the impact of featureization.
Okay, so now we run parallel 4. We do exactly the same settings there. And with a bit of luck, we'll get a new... in fact, I'm going to stop that because I didn't delete the trace file from the previous run. I'm going to wipe all the profiles and trace files because I'm still not sure if it actually cleans up if you restart with the same settings. So I'll do that. And whilst that's running, I'll go back here and play with this. Now, there should also be some PAPI performance counter data in here. But I haven't tested this to see if it actually generates what I'm looking for. And I don't see anything on there. Okay, there's nothing there. I don't think we'll get anything useful out of that either. Because I don't think it stores that task call tree. How many different? We've got, goodness, that task there, I'm going to close that one and try and zoom in on just this.
This is
one here.
accumulated.
It's interesting that there's only 14 microseconds total time spent in that set.
Yeah, because it's just an applied, so here you can see that the channel is so efficient that it doesn't even show up in the profile.
I'm trying to select it, but it's so small I can't see, because if I could select it, then I could change the color of it in the plot, and we would see where the communication steps happen, but I can't get the mouse onto there to actually see. If I select that one, I can change it, but this one there. I want to see where that appears in the main. There must be some in there somewhere. Don't see any. Okay, meanwhile, okay, the other one is finished, so what I will do is I will now copy that over as stencil 4. And in here, I will say File, Open. Just check that's finished copying. Okay, it has. And stencil 4. Now what we're looking for is a pattern where those gaps, okay, now you can see those gaps have been filled basically, and this one, because it now has a future in there, has actually got a data flow because you created a data flow, and that now actually has a name inside it. And what I'd like to do is, I should probably do a comparison. If I close this one and I go back to I say don't save that, and oops. It's, okay, don't panic. Okay, that was the original one, and what I want to do is I want to do a comparison, and I want to compare that one with stencil. Okay, I have to open the other one as well. Okay, fair enough. I didn't realize I have to open both of them. And then I can do a comparison. I say File, New Comparison, and I can compare the two of those in one plot, and then I hope we can see the difference. So you can see the total. I mean, we did exactly the same job size with the stencil 2 and the stencil 4, but where stencil 2 was basically waiting in between steps, stencil 4 was filling those jobs in because we have, this was not oversubscribed, was it?
No, this is just futurization.
This is just futurization by breaking stuff into tasks and allowing the runtime to just fit things in where it wanted to, rather than having the synchronous operation. We've instantly, I mean, that's actually quite superb. It's just completely, it's completely halved the runtime, basically.
Yeah.
Well, it went from 19.8% or whatever, 8% or whatever, or something. So it almost halved it. So it was an almost. So now can we do this? There's actually, well, that's why oversubscription doesn't help, because look, there's nothing to fill really in that second. I don't know how to switch back to that one I wanted. Okay, I mean, there's no spaces here to fill, which is why the oversubscription isn't doing you any good, and why your graph is dropping, because the gaps here are so small compared to the...
Well, it changes when you actually add communication. So if you...
Well, this was 4 nodes.
Yeah.
But I'm not sure that we're looking at the trace file from all 4 nodes. I think we're looking at the trace file from just 1 node. I suspect Apex is only writing out 1 trace. Yes, question at the back.
No, that's the gap between the different steps of the computation.
I'm going to give this to you guys.
The whole timeline at the beginning of the
Yes.
Futurization, there's a gap. Is it for initialization of the futurization, or?
He's referring to this gap up here, because this one takes longer to start. And I don't know why that would be a longer startup time on that one than that one.
Me neither.
It would be interesting if that would also scale with the amount of nodes, for example. Or
well, we can tell you that when you start an HPX job up, when it starts, it does that component registration, and it has the factory stuff. And there's also, for the serialization, it exchanges, each node kind of exchanges the information about what function maps to what ID, so that when you call a function on a remote node with an ID for this action, it's the same on all of them. They kind of exchange information to make sure everybody's got the same setup. And that does mean the startup time is a bit... I've got a trace, actually, that I did yesterday from... And I'm not sure if... Let me try that one. I'm not sure if I deleted it. In this one, you actually see... That's not the right one. Hold on. It must be that one. OTF archive 1. Yeah, look at this one. You actually see, this is the algorithm running. In this particular case, it was my latency test, I think, that I ran. And the test itself is so short that this is basically the work that's going on. And the startup of the runtime is this. Yeah. So this is the bit where the load components is setting up. This is the very initialization when HPX calls init. And then here it's going through a setup phase where it's loading all the factories and getting everything ready. This one, probably if I zoom in on it, you'll see it. But on this is like a 1 second time frame. So on a job which only took a fraction of a second, it's quite noticeable. Whereas on one of the ones which takes a bit longer, and I don't know which one I'm looking at now. This is, I also don't want that one.
It might also be file system related, that the gap. So when we start up, we look in the different libraries for certain symbols. So it might be that file system hiccups actually kicked in. So.
But yeah, in general, that startup time, the more nodes you add, the longer it tends to be. And the idea, and that's something that he's been working on quite a lot recently. And the idea is to make sure that it doesn't turn into like an hour when you start on 1,000 nodes. As long as, I mean, if it's 30 seconds on 1,000 nodes, you're okay.
I just wonder this gap there of the futurization is just because of the futurization. I mean, the longer gap there.
I don't think so.
There shouldn't be any difference in the startup on these two, to be honest. It might just be, I mean, it might be the way Vampire is displaying the traces relative to some starting, because there doesn't appear to be anything actually happening before here. Unless, there is a tiny bit of activity going on there. And unfortunately, because the apex isn't, I'd like to know what these tiny ones are. They're very, very short, whatever they are. That is bind prefix action. Do you know what's going on in bind prefix action?
That's the actual component registrations.
So that's, yeah, so what's, the problem is that the Apex library is hooked into some of the major things, but some of the minor stuff during startup, these gaps here, I mean, there's something going on in that gap, but I can't tell you what's happening. And also, because it looks like we're only looking at the trace from one node and not the trace from multiple nodes, that it could be that it's waiting for one of the other nodes to do something. But the, this part is quite an eye-opener. It's interesting that these tasks here are the same size as these tasks, but they've been packed in so much more nicely.
No. It would have been strange if they were a different size.
Yeah, that task there is now the equivalent of that, but it's running inside a data flow. And they should take basically the same amount of time. Okay, right, what's next on our to-do list?
The performance counters?
Performance counters. Well, if I were to run the first job that I ran, which was the parallel 2 version, and I were to say HPX print and print counter. Anybody who can remember this syntax is a hero in my view, because you have to cut and paste from a demo. Locality, hash star. Can you read it to me and I'll?
Hash star / worker - thread hash star.
Hash star.
Curly braces.
Curly
closing,
braces. Oh, curly.
Slash.
Closing.
Closing,
slash.
yeah. Idle dash rate.
Idle dash rate. Done?
Yeah. Closing quote.
Closing quote. So what that is doing is the dash star is like a regex. So it's saying for every locality, print out the worker thread, every worker thread on every locality, print out the idle rate, and it'll either crash with an error message or it'll run and it'll print that stuff out. We'll see in a moment. And we're expecting, since we know the second one runs about twice the speed of the first, we're expecting an idle rate around about 50%, yeah?
Something like that.
Otherwise, the other one wouldn't be able to run twice as fast. So I would look idle rate 40 to 50% probably on this. And if you run your test and you get an idle rate which is anything more than 5 or 10%, then there's scope for improvement, really. If you get 90%, which is what you normally get on the first run.
It's really hard and distributed, really.
Yeah.
So this is measuring you do within the library?
That's instrumentation within the library, yeah.
Yeah, in fact, in the...
And this you only have if you do the profiling version of HPX, right?
Well, in fact, the idle rates are turned on. On the release build that I did, I turned them off. But if you do this, if you turn on thread idle rates, this is one option which I nearly always have turned on, even in release mode. It adds a tiny overhead, but it's the kind of overhead you like paying for, because, I mean, if you lose 1%, but you get all this debugging kind of information, it's not 1%, it's a fraction of a percent, I'm sure. But basically, every time the scheduler is going through its loop, and it's pulling a job off the queue, and then it's basically executing that. when it gets to the end of a task, it starts its timer, and then when it executes the next task, it stops the timer, and then or rather it marks the time, and then when that one finishes, it marks the time again, and it's keeping a total running total of how much time is in somebody's work and how much time is in this scheduling loop. And what you see when you come out is basically what we call what's referred to as the idle rate, which is the time when you're not doing useful work. But there's also you really need to look at the documentation, because there's tons and tons of counters, and they all have. Okay, so the way to read the idle counters is the granularity is 0.1%, and we got an answer of 48.22. So it's 48.22. We've multiplied by 0.01. So it's not a 0.01% idle. It's a 48% idle on that thread, and it's a 50, which is actually pretty much in the ballpark we guessed beforehand, because we looked at the traces, and we saw the runtime. So things are looking about right. And you can see all these threads. It tells us that these are the worker threads on locality 0 up to there, 16 of them. We had hyperthreading turned on. Maybe we should disable hyperthreading. We might.
Maybe, whatever. I disabled them in my scaling experiments. So
what we're seeing is 49, 50, 48, basically 47 to 50 range on that node. And then on this node, it's pretty much looking the same on all of them. And occasionally...
We really have to work on visualization of those beasts.
Yeah, if that could be pumped into Apex as well and displayed somewhere, that would be useful, into Vampire. And the thing you want to look out for is occasionally you'll see that on locality 0, where you've done your setup, you've somehow messed up, and you'll find that there'll be a thread on locality 0 which is somehow not working the way it should. You want to look for, if they're all coming out about the same, that means you've distributed the work quite nicely. So we'll do the same performance count test, and I'll just put in a parallel 4 here. And we're hoping for like a 98, or it should go from 48% idle down to 2 or 3% idle.
Almost.
Oh, you've just done it, have you? Mm-hmm. And you've got, 0.6%. No, 6%.
6%, yeah.
6, 7, 5. He's just done it, and he's got numbers around 5, 6, 7% idle. So
which is okay.
That futurization shaved off 40% odd. So the nice thing about the idle rate counters is they don't require any external tools. They don't require any fancy tricks. You can just put minus, and it basically profiles itself.
As a rule of thumb, always use features. As a rule of thumb, then you should always use futures.
Granularity matters. Granularity matters. So futures come with overhead, right? So if you always use futures, I mean, as we discussed this morning, if you would put each point update into a task, right? So you would create one future per point update. It would cost you a lot, right? So you would lose performance. So you always have to weigh there's no real rule of thumb, but if your algorithm, like this boundary exchange, is suitable to have communication and work being overlapped, right? So, I mean, what we had in the, getting distracted. So what we had in the first distributed version, right, was synchronized. So we waited for the communication, then did the line update on a single core, and then ran it in parallel, waited for the parallel loop to finish, and then did the other communication and other line updated serially, right? So we added a large portion of serialized code in there, right? So, well, I mean, if you look at it that way, it makes total sense that it was just slow, right? And if this serial portion of code would have been small, right, then adding a synchrony or parallelism wouldn't have bought you much anyway, because the serial fraction would have been so small. And the overhead you added with creating new tasks and the future and everything would have actually been more than the benefits you get from additional concurrency and parallelism, right? If that makes sense. So if you
we've got a winning. The winning thread here is about 1.4% idle, and the losing thread is about 6 or 7% near the start somewhere. There's a bit of a range. There's a bit more of a range on this one, but it's all within. It would be hard to tune it to get better, I think.
And now, what's interesting now is if you increase the number of local partitions,
Okay,
right,
let's.
the idle rates will go up again because the granularity of the tasks decreases, right? Or you get more finer grained tasks, right? And eventually the idle rate will go up again because the overheads inside of the runtime system to do the work stealing, to do the thread scheduling and everything will go up, right? You have a small contention inside of the work stealing because you have all the atomic operations and everything. And if a lot of threads, a lot of cores try to access the same atomic, right? You add contention, and it just adds up in the execution time, right? So if your tasks are too fine-grained, then you will lose some.
I've started another run with 4 local partitions per node, but I will, when that finishes, I'll copy it across as 4-4.
So you have to significantly increase the number of local partitions. I just ran with 16 and it didn't have any change. It actually ran a little faster still.
Well, I will do a comparison between the trace of the futurized version with 1 local partition and the futurized with 4. But since they both came out, it doesn't seem to be doing anything. Did it actually? I'm not seeing the dots appearing on the screen. Did it?
I don't know what you're doing.
Let me restart it and see what happens. Okay, I ran it with that command line. I said, do that, do that, do that, and local partitions is 4. And it did the apex dump at the start, but then I'm not getting the ... lines to show me that it's...
That's strange. Oh, the stencil 4 doesn't have the dots.
Stencil 4 doesn't have the dots?
No.
Ah, okay. Because it's futurized, and so you can't do a dot at the end of a... So you need a continuation at the end of something which prints out a dot.
Right, and I decided, nah. There would have been an example for too much overhead, right?
Okay, I restart that.
It's not going up.
So whilst we have an idle moment, the tricky part of debugging the HPX applications is that if you get a seg fault somewhere in one of your tasks and you attach the debugger and you're able to actually see where that seg fault happened, the problem which I find is very nasty is that when you debug traditional code, usually you look at the backtrace, you see the stack trace, and you see, this was called by here, was called by here, and then you go back to some function, and you think, of course, in this function, I'm doing something wrong, and that triggered this error. And usually just seeing the backtrace and maybe a couple of the registers or the variables is enough to, you instantly think, of course, yeah, that shouldn't be in that part of the code. The problem with HPX is that because you spawn something as a task, and then it goes into a queue, and then it gets pulled off by the runtime some point later. When you attach the debugger, your backtrace basically only has one function deep, which is useful, because you've got the task you're in, and then the stack trace from that task goes back to the runtime, which goes back to the runtime, to the runtime, to the runtime, and you get this tree of all the runtime stuff that instantiated all the schedulers and everything. And you have a really hard time working out sometimes, because you'll often find that if you're in iteration n of a loop and you get a seg fault there, and you look at the stack trace and you think, and you can see exactly what's gone wrong. But if that loop has been broken into task, 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 you don't even know which iteration of the loop you're in when you look at the back trace, because you just don't have that contextual information. For me, this is the number one hard thing about the debugging, is finding out exactly why that particular task crashed when 30,000 other ones didn't crash. And I'm hoping that Thomas here will show us some fancy GDB tricks. And
I don't have a solution for that.
Okay. What was I going to? Oh, I remember. I was going to do a compare. I just want to look at the idle rate on this one. The idle rate is now. Okay, this is wow. This is 0.79, 0.9, 0.6. That made a big difference. That went. We had a 1.5% up to 6%, and now we're getting everything is less than 1% idle. So if we've saved 5%, we should see a 20th of the time. So we should see the total trace should be about 1/20th shorter with a bit of luck. So I'll zip over here, copy
You shouldn't forget that increasing the number of partitions also increases the work that you need to do, right? So
so we're losing. Okay.
So it's still a little trade-off, right?
So we're executing stuff with less wait time, but we're actually doing slightly more work.
Right.
True. So we may not actually see a total speed up. And okay, I'm just going to close these down because I don't know which ones are which anymore. I find that if I have more than about 3 windows on the screen at a time, I get confused. Got any more of those hanging around? Okay, so back to Vamp here, over here, and I'll open Stencil 4 we like. And then I want to also go up a directory, and I want 4-4, which is 4 partitions per node. And then I want to do a new comparison, and I want to compare those two, and then make that full screen and see.
It's almost the same as you see, right?
Yeah. Oops, didn't mean to do that. How do I? Oh, that's some more interesting function summary on here. That's actually useful information. Okay, so there is, I opened a window on the last session. I'll close that down. In fact, I've got 2 function summaries. Why have I got 2? Because it's comparison. Okay, so yeah, this second version, and again, the startup time here, look, if we knock that gap off there and shift that one here, there's a very slight difference, but it's interesting, there's a strange pattern here of...
No, in general, you don't see any gaps in the when you increase the number of local partitions, right? Or not as much. So you are able to fill a little bit more gaps.
Did we make individual tasks longer when we switched to partition 4? Because these ones are definitely bigger than the... Actually, I should have looked at the actual length in terms of time. There's one. That's 1, and it takes about. I can't see where the start and end of it are anymore. I lost it. Okay. Well, anyway. So we basically showed that increasing the partitions on something that was already pretty efficient didn't make a huge difference.
It should make a difference at scale, I think, when you add more network communication.
Yeah, I'd love to do a run now with 1,000 nodes and do the same plots, but I don't think we would have time to get the job in the queue, and I should have done that last night.
And the thing is, you only communicate with 2 neighbors, so the communication doesn't weigh in so much, right?
Yes, it's interesting, actually, the communicator that Thomas set up, where he basically created a communicator which connects to up and connects to down and gets those registered names so that every node registers an up and a down if they're not the boundaries. It's a bit like when you do an MPI com create and you're creating a custom communicator for this pattern, except that you don't actually have to do a com create in a sort of synchronized manner. You basically just get whichever node you want to talk to, and you've created a pseudo communicator out of that channel pattern.
It's like a neighborhood communication, right?
Okay, I am going to hand over to you if you want to show DDT or anything. I'd definitely like to see your GDB
skills.
GD, I'd like to see the pretty printers that Parser has been working on,
Okay.
if you've got those available.
Do we have a break?
Do we have a break? What
Oh,
time
it-
is the break? 1:15 to a break in 5 minutes.
Let's
we-
do a break, then I prepare the pretty printers and everything.
Okay, we do a break now, and then we have, is that right, 2:30 break time? 1:15 till 2:30 sounds? No, it should be 2:45.
2:45. So
Should be
let's
2:45.
let's get started. So,
Give you the,
yes. So,
you're going to want to move a bit closer, and I'll want to move away.
so.
What kind of backends are supported? So what kind of backends are supported so far by HPX, like CUDA one, and then host, and then there's work done for other.
What kind of backends are supported? Okay, host CPU is
CPU,
supported.
obviously.
The mic works out of the box because it's a CPU,
Okay.
and you just have more threads.
Don't have to do
CUDA,
anything special there?
beg pardon?
Don't have to do anything special there to manage the.
Probably a couple of compile options, but
Well, it depends on which PHY we're talking about, right? So you have the coprocessor PHY, right? But on the even if it's a coprocessor, right, you can still run applications as if it was a processor. There's a regular Linux there, right? So you just compile, cross-compile, right? Cross-compile and set up your application and be done with it. So we've done some experiments on Stampede, for example, the machine in Texas, right? One of the publicly accessible Knight's Corner supercomputers, right? And so we had one locality on the PHY and one locality on the host, right? And this was pretty decent. So, I mean, you had still the usual problems that the communication of the PHY was just too damn slow, right? Which they fixed in Knight's Landing. But other than that, we have absolutely no problem scaling up our threading system to 260 cores.
And Knight's Landing also have different memory hierarchy, right? Is there some special allocator done, or there's some work done on that? There's some work done on that direction.
Knight's Landing does have, well, it depends on the configuration your Knight's Landing is booted with, right? So you have the, well, more or less two different configurations. So one where you have the whole address space in a uniform manner, where you have the usual, now I'm confused. So let's start, so you have the 4 NUMA domain configuration, right, where you use the high bandwidth, where the high bandwidth memory is turned off, right, but you still have non-uniform access to the different memory locations. Okay. Then you have the configuration where you really have one NUMA domain, and the PHY somehow manages it by itself. I don't know. And you can still configure the portion of this high bandwidth memory to what you are able to use, right? So the question is, I guess, how do I use the high bandwidth memory? If there are special
Only
allocators.
if there's some work done on that, or if there's some plan to optimize the
Right.
backend for that, like for the CUDA one.
Right.
So-
So if you just run on the 4 NUMA domain configuration, then it's like just a regular CPU with 4 NUMA domains, right? If you want to use the high bandwidth memory, you have to do some special work. We have some initial work done. I don't think it's working yet, so the high bandwidth memory is a little bit special to regular main memory, how to access it, how to pin the pages to the high bandwidth memory, right? But there definitely will be something that you can really use the HPM
Okay.
directly.
Because I guess there's for all the different backends, you need a way, like some way of like efficiently use, I don't know, some scratch pad memory or something that can be specifically implemented for that part. So.
Right, right. So for the scratchpad memory, yes, we want to have something for that, so you can allocate things directly on the scratchpad memory. Other things we're looking at is the heterogeneous computing stuff done by the Kronos group with SYCL, and also the stuff done by the HSA Foundation. Right? They provide similar technology than what NVIDIA provides with CUDA nowadays. Right? So you can. So the hope is to be able to do something similar to what we've done with CUDA, but that's still work in progress, and we haven't anything that's even experimental. So highly experimental with only the guy who programmed it knows how to use it.
For the KNL, because we now have KNLs here on site, I will be testing those out at some point, and if and when I come into the kind of problems where I'm not getting good cache coherency and I need to do work, then it may well be that we create a target, which is a KNL type device, and then you get an allocator from that target and executors from that target, which you then run tasks on, and that's something which we'll discover in the next few months, I'm sure.
Yeah, it's a pretty hot topic.
Okay, so that's your task.
Well, it's not my task, but both within the work I'm doing on a daily basis and on one of the projects in particular, for example, the machines for human brain, we have KNL on, and at some point I'll need to get my stuff running on those, and I will be doing benchmarking, and I'll discover that exactly these problems. So. I'm just giving it back.
So I just wanted to mention that I increased the number of partitions, and I can't get the idle rates back up for one reason or another.
You've got 2%, 5%.
No. So it's gone up a little bit, but the performance is still in the same order, so yeah. So you should eventually see that it's rising again. Yeah.
Oh, and I didn't mention that if you wanted to try generating those traces, you can compile your stuff with the profiling module and just do module load Vampire in order to actually visualize them, and it should work on Dane. I just used the Vampire on the laptop because over the Wi-Fi it's a little bit flaky.
Right. Okay, so before actually going into GDB debugging or DDT debugging, I wanted to demonstrate or guide you through the compile errors that you might run into, right? So one of the goals of C++ interfaces is that you get errors at compile time if possible, right? So that you really don't need to run your application and realize, oh God, it died on me. How do I debug it? So interpreting error messages, fixing compiler error messages is part of debugging, I think. And some people are often frightened when they run into error messages from the compiler, which are a few pages long, right? Rightfully so. I would even consider that those error messages are bugs in some way or another. There are techniques to shorten those error messages, but eventually you still have some instantiation depth of the template. So there's no silver bullet to get around there, right? So let's look at some examples. We haven't actually prepared anything, so I will just reuse the Hello World program. can you all read it fine? I can increase the font size a little bit. So one thing is, of course, one source of errors is usually you forget to include headers, right? So I just removed the header files. So let's see what's happening. Doesn't have bash completion in there. So on some machines, you have bash completion.
You don't need the exe for our tutorials, because we haven't used the...
So on some machines, you have bash completion. So if you type make and then hit your tab key twice or a few times more, then you get actually an overview of all the targets, and then you can use the completion in a similar way you're used to with using tab completion with the directories and files. So let's see what's happening if I don't have the right includes. Ta-da! And I see a lot of errors. So this is already a little bit messy, right? So let's try to get some structure into it. So what I usually do is I pipe the output of the compilation process into a pager, so usually less. And then I just wait until the error pops up, right? So now I have 6-7 lines of error message. So, yeah, and I just removed the includes. So that's essentially C++ for you. Unfortunately, it doesn't stop at the first error, right? So first piece of advice is look at the first error message first, right? And you see that the error message is clear. It says that get locality ID is not a member of HPX, right? So it's obvious that I forgot to include the header file. So I just reversed the change, and now it should compile again. So let's say I have a typo in there, right? So I forgot to have to type the D, right? The error message should be the same. Get locality I is not a member of HPX, right? And then the error message looks very similar to the one where you have forgot to include. Fortunately, compilers are pretty advanced nowadays, and they do fuzzy searching of the symbols. So at first you get some warnings, yay. So you have warnings. I know that I have an error message, so I just search for error here, right? This particular version of GCC is not that articulate then.
You're using 5.3?
So starting with 6 point something, you usually get something like, did you mean blah, 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 and they did some fuzzy searching on the symbols that are parsed, and then it suggests to you that, did you mean get locality ID, right? And that's what modern compilers can give you. Unfortunately, this one not. So let's continue with more error messages. Okay. So let's say we have a future, right? Let's say future int. And we have another future through make ready future, which is a future string. Okay? Those are not.
Are we seeing verbal? Verbal name?
Where?
Should we put a name there, no?
Oh, yeah, sure. Thanks. Okay, this should give an error, right? Because a future string isn't convertible to a future of int, right? So let's look at the error message. And it will not say directly this future is not I made a mistake again, typo.
I managed to find the communication tasks in there. And I should probably...
Make them red or something.
Well, I've already got a red task in there. You just can't see very many of them.
You're getting distracted. Huh?
Yeah.
Oh, this is nice.
Yeah, it's kind of cool, isn't it?
It's awesome. So you have to show. So, sorry for the distraction, but John.
There, look, these red ones. The red ones are very sparse indeed. So I was just delving into the, just for a moment. I was delving into the trace file that we generated previously, and I was looking to see if I could find the channel set and get functions that were actually doing the. I probably need to drop out of full screen mode and then re-enter full screen mode because I found some tiny tasks in there which I've highlighted in red, and there's also some other ones which I've marked in green. And if I zoom right out, then you'll see that those are the communication steps. And there's quite a lot of synchronization between them. There's some chunks here where there's lots of work going on, and then there's bursts of communication. But essentially, these are filling in some of those spaces that we saw in the very first plot. And I was just skimming through looking, and it's just nice the way Vampire, you can see up here on this top trace how Vampire is kind of, it's giving a representation. There's basically 1, 2, 3, 4, 5, maybe 6 bursts of activity, and it's kind of plotting those somehow in the colors up there, which I had. You see this all the time, do you, Jean-Guillaume? Because I don't use Vampire very often, so I didn't realize it did that. But you can see the communication, and I was looking through here to find, there's a tiny red one in there, which is when the channel is set, or rather, let me check that red one, if I can.
This should be get, huh?
I think it's get, isn't it? The get generation in there, and the green ones are the set generation. And explain to me why the green ones are so much bigger than the red ones?
In that case, because the setting is coming before you get something. So the setting does all the work.
Yes.
Creates the promise.
Creates the promise, copies the data in if necessary.
Right.
And the get just gives you the reference back out.
Yeah.
And it would be the other way around if you were calling get before the data had arrived and it was blocking in some sense, or it was creating and doing all the construction up ahead. Yeah, okay. But this is quite nicely overlapped. There's no hard synchronization points in here. I must try and do the same plot now with the non-futurized version, which might be over here. No, I need to open the non... I need 4. And I need to... Jean-Guillaume, can you tell me, is it possible for me to copy my color settings from... Ooh, no, that's the wrong one. I'd like to copy my... I've opened stencil 4 twice. No, I need stencil 2. Yes, beg your pardon. I need file, recent stencil. I need stencil 2. That one. Okay, now I want to do the same. Yeah, I'd like to see the same.
This is so awesome.
Same red and green bits. But they must be tacked onto the end of these little. Yeah, they should be things like that, little tiny. If I can zoom in a bit further. So if I select that one and I color that, what did we color? Did we have for get? Did we have red for get?
Red for get.
And we had green for set. There's an interesting one. This is an internal to the parcel port network. This is the actual send action which passes it into, in this case it's passing it into the MPI. So we better give that a special color as well because
awesome.
I'll make that black.
That's
and
cool.
And now the problem is the tasks are so
I have
tiny.
to use it so more often. It's just
the tasks are so tiny. It's quite hard to find them.
No.
So
the score P is free, right? And Scorpy comes with a Viz tool as well, doesn't it? No? Ah.
Well, I can't for the life of me find. But we should be able to. But that's interesting because look, we have a get here,
But no
we
set.
don't have any. No, I need to zoom out and then I need to find the set in here because it only shows the ones that are visible in the. Oh, so there's actually quite a lot of tasks that they're all so tiny. There's the set,
There's the set.
but I don't know how to actually change the color because the bar is so thin that I can't.
Can
put the
you
mouse on it.
right click on the channel set? Filter function and then.
Oh, it's here. I can do it now, and it was sort of reddish on the previous one, but
it doesn't show
it
up.
doesn't show up, which is kind of sad because I'd like to see if, you see, I'm expecting there to be some sort of synchronization point between this one and this one. There should be something like a color here and then a color here, which we could match to
But
each
you
other. But
probably, it's a little sad that you can't see the other localities.
yes, I'll work on that.
Uh,
Okay, I'm giving this back to you now.
okay, so more on error messages during compilation.
Tea time if everybody wants to break.